And now let's go over the limit of a sequence. So a sequence such as the one in example 1a, where it's an equals n over n plus 1. It's right here, so 1a, n over n plus 1. You can see this number's right here, 1 over 2, 2 over 3, 3 over 4. You see it's always going to be, well, less than 1 there. I'll show you further here. Yeah, this sequence, it can be pictured either by plotting its terms on number line or by plotting its graph as in the figures below. But first, let's just write this out again. So if an equals to n over n plus 1, so then the sequence is going to be like this. We'll have 1 over 1 plus 1, the first term is 2, then 2 over 3, then 3 over 4, then 4 over 5, and it keeps going on until we get eventually we get something even like 100. Yeah, whoops, dot, and then 100 over 101 over 101, dot, 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 and then all the way it keeps going on, n plus 1. So in other words, the denominator is always 1 larger than the numerator. So in other words, it will never be greater than 1. So it's always going to be, it appears like it's approaching 1. Thus, what we end up having is an infinity over infinity plus 1. So in other words, it's approaching 1. Now, if you were to draw this on a number line like this, what we have is initially 0, and I'll write this as an. So that's initially, there's the 0, but at the first term is 1/2. So let's say 1 is over here. Actually, I moved it around. Let's say we have 1 over there. So the first term, a1, is going to be at the half. This is a1, and the second term is at a third, so that's going to be somewhere, let's say third would be somewhere around here. A2, this is 2/3, like that. So I'll just erase this part. Well, yeah, just assume it's there. So then the 3/4, now it's going to be at the 3/4 mark, so A3, and then the A4 is 4/5, and 4/5 is going to be somewhere around over here, A4. Actually, it's going to be a bit bigger than that. It's going to be somewhere around here, A4, and then A5 would be somewhere across like this. And as you can see, it just keeps getting, well, closer and closer and closer and closer and closer, like this. And it keeps getting closer and closer to this 1, and there's going to be a wall here that never gets close to it. So it keeps getting closer and closer to 1. So yes, it's like forced upon this wall there, right there. So yeah, it appears to be approaching that limit. And in fact, I'll prove it is. Yeah, further down in this video. And also now, if you were to graph this in a different way, like this, let's say we had n, this is an, just in a graph form, so this is 0, and let's say we had, this is 1, so there's the value 1, let's just draw this line across, let's draw this line across, 1, yeah, so the first term is going to be like this is just going to be 1, the first term is at the half. So there is at the point right here. The second term is 2. That's going to be at the 2 over 3, be somewhere across here. Then we have the 3, 4, 5, 6, 7, and then it keeps going on. There's a 3 is going to be at the 5th. There's the 4th, and then there's a 5th, there's a 6th, 7th, and the 7th is, this height is going to be, well, A7. Which equals a 7 over 8. So just 1 more than the numerator. 7 over 8. And it keeps getting closer and closer. So yeah, it's just keeps getting closer and closer to that line there. Yeah, and now note that since the sequence is a function whose domain is the set of positive integers, as you can see all these positive integers, its graph consists of isolated points with the following coordinates as I drew above here. This one's going to be 1, 1/2. So there's 1, 1/2 is at that point. And then, yeah, they're going to consist of something like this, 1, A1, and then we'll have 2, A2, and then 3, A4, I mean 3, A3, and so on. And then we have dot, 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 then we have n, an, like that, dot, 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 keeps going on and on. Yeah, now from the above figures, it appears that the terms of the sequence an equals n over n plus 1 are approaching 1 as n becomes large. In fact, the difference, if we were to write 1 minus that sequence, 1 minus an, which equals to 1 minus n over n plus 1. And now what I'll do is just multiply this top and bottom by n plus 1. This equals 2, well, n plus 1 over n plus 1 minus n. So this is, I just multiplied that by n plus 1 on top and bottom, so same common denominator. This cancels, this cancels. This equals to, well, 1 over n plus 1. In other words, this value right here, this is pretty much approaching 1 over infinity as n approaches infinity. So when this gets super large, in other words, it's approaching 0. Yeah, so basically any number you put in, you can put bigger and bigger, it's just going to get smaller and smaller. So then basically that difference, the difference between the sequence can be made as small as we like by indicating n sufficiently large. In other words, that difference is going to be getting smaller and smaller. It's going to be getting smaller and smaller. And yeah, smaller and smaller, closer to that 1. So there's 0 difference eventually. Yeah, as the limit goes to infinity. So we indicate this by writing the limit as n approaches infinity of n over n plus 1 equals to 1. And in general, the notation, so this notation, limit as n approaches infinity of an equals to L, limit. Yeah, so this notation means that the terms of the sequence an approach L as n becomes large. And notice that the following definition of a limit of a sequence is very similar to the definition of a limit of a function at infinity, which was given in my earlier videos. So recall first the definition for limits at infinity from my earlier videos for a regular function. So let f be a function defined on some interval a to infinity. Then the limit as x approaches infinity of f of x equals L means that the values of f of x can be made arbitrarily close to L by taking x sufficiently large, getting larger and larger, and then the value gets closer and closer to L. So this is very similar to the following definition for the limit of a sequence. Definition 1: a sequence an has the limit L, and we write limit as n approaches infinity of an equals to L, or you can write this as an approaches L as n approaches infinity. And this limit, we have this limit if we can make the terms an as close to L as we like by taking n sufficiently large, and again, pretty much identical to the earlier definition for regular functions, and also for defining convergence. So if limit as n approaches infinity an exists, we say the sequences converge or is convergent. Otherwise, we say the sequence diverges or is divergent if it does not converge, or if the limit does not exist. And the graphs below shows two sequences that have a limit L. And you could graph it like this. This is one of them. Let's draw it like this. This is n. This is an. This is 0. And let's say we have a limit L like this. Then what we have is to separate each points. So remember, it's integers, and here is one way of writing it. So this one would have a limit, would look like this. So as you see, this one's approaching it. It goes up above and comes back down, approaching it, and it's approaching that limit L. So that's one way. Another form is you can even have it like this. It's still going to be the limit an, and then we have the same L like that. Let's try it even further. So what we can have is, again, similar, but let's say we have something like this. It goes up and up. So this one, it could oscillate. And yeah, as you can see, this one, it's just oscillating around this. Oops, I'll draw this a bit better. It's going to be something like this. Oops, yeah. Yeah, so you see this one is getting closer and closer to this one. So this is getting closer and closer, but it's oscillating around the limit, but it's still getting closer and closer, and both of these have limits L. So both have limit as n approaches infinity of a n equals to L.